So okay, we're continuing with the proof that we're in. We're in a proof of Cauchy's theorem. Okay, so I'm just going to continue straight on. So we're trying if we can find an n is an element of the natural numbers, such that Rn is contained within the ball, which I'll just denote B because I've run out of space. Then it's obvious that this second bit of the condition is true, because any rectangle that's further along in the sequence than this rectangle is contained within that one. And by, I don't know, the basic axioms of set theory, if you've got a set that is contained within another set, if A is contained within B and B is contained within C, then A is contained, then that implies that A is contained within C. So basically, if I can find a rectangle such that it's contained within B, then all the rectangles after it must also be contained within B. So all I now need to prove is that I can find a rectangle which is completely contained within B. Well, that's not too difficult, because what do we know? All we know so far is that Z star is an element of no, I almost wrote the real numbers then. All the rectangles is an element of Ri, for I is an element of the natural numbers, or indeed 0. Or 0, alright, or 0. So basically this point is the intersection of all of them, so I could actually write that. Z star is equal to the intersection I is equal to 0 to infinity of all of those sets. Ri. And the theorem from topology that I don't know how to prove is that such an intersection is non-empty. Such an intersection of nested rectangles in this way is non-empty. And nested, just in case I don't know if I've defined that term, nested just means that you have one set in the sequence and the next sequence. It means where did I write it? It means that property there. That property there. That the next so when you've got a sequence of sets, that the next set in the sequence is completely contained within the prior set of the sequence. Okay, so let's go on to the next page. Right, so how do I prove? So we need to prove that there exists a rectangle in this sequence such that it's completely contained within the ball around Z star. Well, all we need to do is, if I take an arbitrary rectangle, we'll call this Ri, and what's the maximum distance? What's the maximum distance any two of these points can be away from one another in this rectangle? Well, it's obviously the diagonal distance. So all I need to know is what is that diagonal distance, and then if that diagonal distance is made less than epsilon, then that would imply that it has to be contained within the ball of radius epsilon around Z star, because Z star is somewhere within this rectangle. So if I put Z star here, it can be anywhere within that rectangle. We don't know where it is. But then if we draw an epsilon ball around here, and that epsilon is greater than the biggest possible distance that any two points within this rectangle could be away from each other, then all of the points of this rectangle must be contained within the ball, because the worst possible scenario is that Z star is one of these corner points, and then this point is the furthest point away from it, and we need that point to still be contained within the epsilon ball. So if Z star was here, we'd have to draw an epsilon ball around there, wouldn't we? And we'd need that point to be contained within the epsilon ball. We're here, so we can draw. If it was here, we were in a slightly better situation, because all the maximum distance of any point away from Z star is going to be less than the maximum distance of any two points in the set. But the worst possible scenario is that Z star is over here, and if this maximum distance here is less than epsilon, then no matter where I put Z star, where Z star is rather, then all the points of this rectangle will be contained within R0. So we just need to prove that there exists an Ri in the sequence such that this maximum distance between any two points within Ri is less than epsilon. So we need to work out what the diagonal distance of a rectangle of a rectangle in the sequence is for an arbitrary element of the sequence. So if this is our R0, we'll call this side L and this side D. Then if we go into the next element of the sequence, what's the well, firstly, what's the diagonal distance across R0? It's just by Pythagoras' theorem, it's the square root of L squared plus D squared. And it's pretty obvious to see just from the picture, because look at this one, this next one. How long is the diagonal distance of the next rectangle along, R1? Well, R1 is one of these, and the diagonal distance is always the same, so it's pretty obvious to see that it's that divided by 2. And then it's pretty obvious to see that if you go into the next one, R2, then that's it divided, that distance divided by 2 again. So it's plain to see, therefore, that the diagonal distance slash greatest distance between any 2 points in R0 any 2 points in R0 in Ri rather is equal to the L squared plus D squared, which is this diagonal distance of our original rectangle R0 divided by 2 to the I. Okay, so we need this distance here, the square root of L squared plus D squared over 2I, to be less than epsilon. So a little bit of rearrangement gives us that 2 to the I needs to be greater than the square root of L squared plus D squared over epsilon. So this is just a number. This is a number that we started with. We started with a rectangle. This is the diagonal distance of that rectangle, so that's a constant. You stick in your epsilon, which is your variable, and you need an I such that this is satisfied. So we could take natural logs of both sides. So I needs to be greater than log to base 2 of the square root of L squared plus D squared over epsilon. So this is the case. This is what we're saying. You give me an epsilon, I will put it into this formula. It will give me potentially some hideous number. I just need to take you... Oh, I should have put that. I is an element of the natural numbers. I need to find you an I, which is an element of the natural numbers, such that it's bigger than that silly real number. Which, is that the Archimedean property that you can always do that? That there's always a natural... If you give me any real number, I can always find you a natural number that's bigger than that. So yeah, I'm not going to prove that. But it should be pretty obvious to see from the geometrical isomorphism of the natural numbers, you know. The geometrical interpretation of the natural numbers and the real numbers. Okay, so where are we? If you give me an epsilon, I can find you an I, such that, so just plug it into that formula, find the I, and the way we've calculated it is such that that rectangle, Ri, and all rectangles beyond that, Ri plus 1, Ri plus 2, they will all be contained within the epsilon ball around Z star there. They'll all be contained within there. And you can do that for any epsilon greater than 0. Epsilon is arbitrary, hence we've proven the definition that we needed for convergence. That's the definition of convergence. We've proven it satisfies that definition. Bravo. Okay, I'm going to end the video there and we'll move on.